All right, so now that we've had some time to look at contrast and how that's generated in TEM, I want to look at some different imaging modes that we have in TEM. And so this is all going to be um, dependent on this objective aperture. So this kind of dictates what type of what section of the beam is allowed to go through and what is not. And we already saw some examples of this in the previous section. So the way that we set up this aperture is going to be highly dependent on what we get. So this is basically just some representations of different methods, and we're going to go through all of these. And then this kind of shows the same thing as well. All right, so let's start with Brightfield images. These are, again, we have a corollary to light microscopy in that this is predominantly bright, and that means that the transmitted beam, so again, this is the up here. This is the incident beam. So the initial beam interacts with the specimen. Some of it is diffracted or scattered, either contrast or it could be mass density. And then some is basically transmitted straight through, right? It's a high energy electron beam, and so a majority of it will go through. So that is the transmitted beam. So if the aperture is set up in which the transmitted beam goes through and the diffracted is not allowed to go through the aperture, then this is known as Brightfield, because a majority is the transmitted, the smaller fraction is the diffracted. And so this is a typical diffraction image, and so you see it's predominantly bright, and you see differences from that. These dark spots, so these are actually nanoparticles. These nanoparticles are diffracting because they're crystalline, and therefore that is the section that's diffracted over here, and so it doesn't make it past the aperture, and so it appears darker. And so that's how bright field images work in general. We can also have what's known as off-axis dark field imaging. Sometimes this is referred to as dirty dark field. I don't know how common that is called, but this is very much connected to the mode we just saw. So this example A here shows bright field. It's the schematic we just showed. Over here, though, it's imagine basically the same sample, the same transmitted and diffracted beams, but what happens here is we're basically displacing the aperture. So we're shifting it to the left here on the screen, such that the diffracted beam goes through and the transmitted beam hits the back. So all we've done is shifted it to the left, or offset that beam. So this isn't very common. This isn't a common way of doing dark field, but it's the same idea. So the transmitted beam is, again, the bright part. It's a majority, and this is the light part. So we'd expect this beam to be predominantly dark, with the areas that were diffracted being light, because that's what's going through this image. So it's going to start out dark, and then the contrast off of that is going to be lighter, and that is the diffracted events. Again, this isn't a common way of doing it, but it is one way in which we can get a dark field image. The more common way to do dark field imaging is centered dark field imaging. And so this is the third schematic that I showed. And so this is where, again, we have a beam with an incident electron beam, our sample, and then the transmitted beam here, and the diffracted beam. So effectively, we've set it up so that the aperture is in the same place, but we've basically adjusted the beam itself such that the diffracted beam goes straight down through the aperture, and the transmitted is what hits the aperture. So we've centered the beam to do that. And we need what's called diffraction mode to do this. So we actually have to use a different mode. So the beam is adjusted in what we call diffraction mode, and this is diffraction mode. So this is an image that's produced showing effectively representation of diffraction, and we can use this mode to adjust the beam. So this might look familiar. This is effectively one of those reciprocal space lattices, and this is a representation of that diffraction in TEM. And so we effectively manipulate the optics in the TEM such that this reciprocal space that's generated from diffraction is viewed on the screen. And so that's what we mean by diffraction mode, a visual representation of that reciprocal space projected onto the image plane. So in doing this, what we try to do is we try to center the objective aperture that I've showed before on a diffraction spot. So let's imagine this is again a reciprocal space lattice. If we're in Brightfield mode, the transmitted beam is the beam that's going straight through, just like you see over here. And then the diffracted beam is all these spots. These are the diffracted parts of the beam. And so if this is kind of our aperture, none of these diffracting spots will make it through the aperture. So what we do is we take that objective aperture and we align it on one of these diffraction spots. So we move the setup in such that the objective aperture that you see here is instead on one of these spots. And so that's the orientations you see here. So this bright spot is still the transmitted beam, but now we're aligning the objective aperture over one of these diffracted beams. So everything else, all these other diffracted spots, will not go through. The transmitted beam will not go through this objective aperture, only this diffracted intensity. And so it's tied to a particular diffraction spot. And that's important because if you think about it, each diffraction spot corresponds to a specific set of HKL planes. So only that set of HKL planes will result in diffracted intensity under this configuration. And so that's what we see here, moving that beam so that we have the center dark field image. So instead of bright field configuration we saw in A, we have this dark field configuration. So the diffracted beam is now going in. So in this, if you think about this setup, anything that was over this one spot, so anything that diffracts in this way will produce intensity because it's going through the aperture. So when you see in this dark field image, everything's dark except for these light spots. And so those light spots correspond to the diffracted intensity. So essentially that set of HKL planes that goes through the aperture. So these bright spots correspond to the right orientation for diffracted beams to go through the objective aperture. So this is what you would see in a diffracted or in a dark field image. And what you're visualizing with the light spots is the diffracted intensity associated with those certain HKL planes of that one diffraction spot. And so, so this might be a little misleading. Dark field can be used quite often. A lot of TEMs now will do both simultaneously, but dark field can be useful because if you kind of take the images I've shown you so far, A and B, they're of the same material, and if we look at this case, all the nanoparticles that I talked about are the dark spots. and they're on top of this light background. Sometimes they can actually be harder to find if they're these fine features like small nanoparticles, and so sometimes you actually see them easier, like you do here in darkfield, when they are bright on a dark background. It's kind of the same idea of a lot of computer screens and phone screens and so forth that are trying to be more accommodating to people with visual impairments. It helps to have a dark background because it's easier to see things off of that dark background for that. So it's kind of the same idea. Sometimes you can resolve finer features easier.